think so much about the input and outputs there that we are dealing with. And in fact, we have seen really big advances by large language models. But if you think about them, they are, first of all, they need a lot of data. And they are also passive learners, right? There is no interaction. You learn them once and then you just take them. So we cannot easily adapt to variation, language variability. All right, so I think in general, what we need, challenges that we need to deal with in the future are to make NLP more inclusive and fair, to support and understand many more language variants, make models also more trustworthy, but on the other side, more efficient with leaner and faster models, but also importantly, make them more human-centered, to include human perspectives and better align also with human values in evaluation. And so we talked about generation and heard about generation. And here is an example of a question that I posed to OpenAI's GPT-3. How do I get from Munich to Venice without crossing the Alps? Okay, so if we asked the GPT-3 now, we get this answer. The simplest way to get from Munich to Venice without crossing the Alps is by train. The journey takes around 8 hours, involves taking a train from Munich to Verona Porta Nuova, then a connecting train from Verona to Venice Santa Lucia. You see, we get a brilliantly fluent and coherent output, but what about the key missing part of the question, right? The crossing the Alps is completely, even though it spits out this answer, this is completely neglected and not a faithful answer. It also lacks common sense knowledge. Now you might wonder, this is GPT-3, but ChatGPT just came out, right? This is kind of an old language model by now. So what about that? Well, I just asked it before here in the room. So today, essentially, this morning, what happened is this. So probably all of you were busy trying to, no, just kidding. But after a little bit of time has passed, I finally got an answer, and you see here what happens. One way to get to Munich without crossing the Alps is to take the train. So essentially, it kind of gives still the same answer. What's even very interesting here is it also talks about passing the Brennerpass, but it involves some mountain driving for the train, right? So you see some more weird stuff happening here. All right, so for generation, there's also a lot of challenges out there. While we are very good in having AI and robots for like journalism and creating this automatic smaller table or text to data output, we really lack good output for longer text, and especially lack of control. We lack factuality and faithfulness, but also creativity, right? And then there is the whole side of social and ethical challenges. I'm not going into any of this here because I'm more on the natural language understanding side, but I think it's important. We will hear more about those topics today, I believe. And so if we just step back, how did we come to where we are? Here is a little summary of our field. So we went, you all know this, so it can be fast here. We went from symbolic processing to statistical NLP, essentially where I also grew up with. And then we had this deep learning revolution around 2015, approximately, where it hit our field. And then the next big step was, in fact, contextualized representations and large pre-trained language models that we are dealing with today. So huge advances, and you see that the timeline is actually condensing as we go along as well. And so if we see this as like a dramatic act, you might ask, okay, we have the rise. Is deep learning like the climax? Where we go next, essentially? Is return or fall? And what's the fifth act in this theater play, you might think? So catastrophe or happy end? So in fact, the question is, are large pre-trained language models all we need? We have heard already previous talks that this is, like also Mark alluded to this, it's not enough. We need to go beyond them, right? I also believe scaling up is not the solution. And here is another view on it, because we have the course of multilinguality. We have models that capture around hundreds of languages, but not much more. And we know that they are not equally represented in these representations. But then we also have the fact that we typically want applications working on different kinds of text domains. And on top of that, we are interested in different tasks. So now that so many more language models are becoming available, how do we even choose one which fits well for a certain task? And so you can think of this as this very huge search space that it's essentially infeasible to look at the whole Cartesian product. So what I believe is very crucial is to learn, in fact, not scale up and train larger and larger language models, because we actually also cannot all do that. But we also need to reinvent and look at how can we learn from scarce data, get a lot of knowledge from little input. And then important questions are coming up like, hey, what about reuse of data, language model, everything we have, and how to deal with breaking this down by taking a modular approach and looking at pieces and how to combine them. All right, so I do believe we need new approaches to deal with this problem. And in the rest of the talk, I will focus on a couple of, some recent studies we have been doing, very small steps in this direction. So I believe we need to go away from big data and learn efficiently from scarce data. And some methods in this direction are to look at incidental supervision, or what I like to call fortuitous data sources. And another idea is, in fact, if you look at what's studied nowadays, here's a nice paper from last year's ACL findings. We have a lot of work in like different dimensions, and you see that they cluster. So it will be also important to go and look at, the cross-fertility of, say, multilinguality with fairness and bias and efficiency, not just look at isolated corners, but do more work across different areas. And so in the rest of my talk, I will gonna go into 3 small case studies of works that we have been doing in my lab. And this is, again, all work by my students. So I'm very happy for what they have been doing. All right, now this is work by Max and Rob, and what we were looking at is dependency parsing. So we are still doing parsing, and we were looking at genre information in dependency parsing. And why that? Because universal dependencies is a huge project which has led to a lot of multilingual or cross-lingual NLP. But if you look at what's contained in that tree bank, then we actually do have genre information. So we try to quantify this information in this UD data. And what you can see is there's a lot of news prior data. And there's a long tail of other kind of domains where you see spoken or social or so on are much less frequent. And we typically only look at the cross-lingual dimension. So this is really across all languages and all domains what we have, quantifying the lower and upper bounds. And what's in fact not less known is that the tree bank providers tag their tree banks with this meta information on genre. And if we try to find information about it, and here's a paper by Jochen Iver and colleagues, and they say, this specifies some amount from different genres as reported by each tree bank provider, but these categories are neither mutually exclusive nor based on a homogeneous criteria, but it's currently the best documentation that can be obtained. So the idea is, hey, we want to document somewhat what kind of data is in these tree banks. And that these are the labels that they came up with. So the question is, can we then use this kind of labels to do better data selection? So if you are, say, a low resource language and training or syntax, you might want to have a good parser for that low resource language, for that specific genre. And now, if you go and train on, say, all of the universal dependency tree bank data, really a massively multilingual parser, you know that it's not working very well for your target. And, okay. So if you have some like Faris lyrics, and you train the model on everything, you know that it's going to be suboptimal. And it also takes a lot of time to do it. But what we wanted to investigate here, can we actually find better suited target training data, so do data selection in order to train the parser on less but more specific data, more relevant data for the problem at hand. And the problem is that, you know, in UD, so here it's illustrated as if every sentence, every tree knows which kind of genre it belongs to. But the issue is that these labels are just at the tree blank or corpus level. So you need to find ways to propagate them to the instance level. So we proposed several ways to do so in order to then select these. And what, like, just as a short conclusion, details are in the paper. What we saw is, first of all, if we take a multilingual model and try to look at these dimensions of variation, we do already see them back to some degree. So the colors in this plot. But if we then propose some methods which uses weak supervision to inject or augment this information, we get much more clearer separation, and that actually helps us to select better training data for this target specific problem. So we could improve zero-shot dependency parsing for the 12 low-resource languages that we had here. And for instance, for Faris, we got an improvement from 61 to 68% LES. And I think this is like showing, hey, there is this metadata. Let's use it instead of neglecting it, essentially. And so this is one example of how we can use kind of fortuitous data to learn models from less data. And in the next part, I will show you an example of reuse, essentially. And so this is a paper that comes up here at the NLP with my PhD students, Elisa, Mike, and Max. We were looking at, hey, you know, there is like large pre-trained language models coming out at a really fast pace. And now if I asked him what language model to choose, he might come up with some answer, right? But it's often really, really based on heuristics or prior work, but because simply training on all of them is infeasible. So I think one of the interesting directions here is also how can we select a large language model a priori, finding the best encoder for a certain task at hand. And this is the problem of transferability and transfer prediction, essentially, transferability estimation. In NLP, that hasn't been done so much so far. There is work on a related problem, namely performance prediction. But here we were interested in, given a set of pre-trained language models and some target data set, how can you estimate a score that then correlates well if you were then to fine-tune the model on. And we took a framework that comes from the computer vision field, so LogMe, and essentially just applied it to NLP problems to see how good it performs. We tested this across 10 tasks, 4 setups, and 7 large pre-trained language models, where we included general ones, but also more target domain-specific ones. And again, a shortcut to the results. So here you see all of the tasks that we tested it on. We had classification tasks. Oops. We had the blue ones are classification tasks, and these one are sequence labeling tasks. And what you see overall, if you take the frozen, we don't fine tune the representation itself. There is quite a good correlation with the final fine-tuning performance. So this is what you're trying to predict from the score that you get. And there is a good correlation across the field where, you know, the LogMe framework is able to identify some obvious or some intuitive things like Twitter, the Twitter language model. Twitter Roberts is good for airline Twitter. But it also finds some less intuitive ones, like Distilbert turned out to be a very good language model for a lot of these sequence labeling tasks. So we were wondering also, hey, how good are humans, or in our case, NLP practitioners, at identifying the best language model from the set of language models that we had. And we found, it was admittedly a small study, just 12 NLP people. And we found, though, that their correlation was worse than the one found by this method. So take that with a grain of salt, but I think it's interesting to see that we're not always the best oracle to choose from. We have a poster on this on Friday if you're interested in this kind of work. All right, and in the last part, I want to touch up on another kind of problem, and that's human label variation. And so typically, you know, we all know when we do annotation projects that we observe disagreement in annotation, and but we largely ignore it and just aggregate the data to find a gold label. So the question is this really a problem? Or should we step back and instead of going the route to the typical gold label, look at information from the multiple or unaggregated data? And so one nice example is in fact a study by Eli Pavlik and Tom Kwiatkowski. They looked at the NLI data and re-annotated it with 50 annotators. So here is an example of a premise and a hypothesis. Amanda carried the package from home and Amanda moved. And what they found is when they let people re-annotate it on a scale, then they saw that there is a lot of entailment, but there is also another, you know, not just a unimodal distribution that comes back from this data. So there's this is an example from NLI, but there is a lot of other work that shows that there is perhaps not a real ground truth. And this is an old idea, so it goes back even by Sissy Alm already pointed it out on subjective task, questioning whether there is really, whether there is an absence of ground truth. For instance, she looked at emotion prediction and so on. And there is now recently an increasing interest in this problem, especially if you think of tasks that are more connected to the human, right? Like offensive language detection, abusive language detection, where it's really, really a very challenging task to get data and just one ground truth, essentially, meaning one perspective. But there's also work on that outside NLP or, you know, here in visual question answering, but also more in the computer vision area, where they start to look into this problem as well. And I want to mention that I talked so far about disagreement in annotation, but this is not always just disagreement. So I would like to propose the more general term, human label variation, to kind of capture the fact that some of it is disagreement, but there's also different perspectives. And there's even tasks where we might want to have multiple plausible answers. So we can all see this as human label variation, which though is something that we think is genuine. And it is clear that we need to distinguish this from plain noise, so like annotation errors. But the question is how to do this. So this is a very challenging, where to draw the line even between annotation errors and genuine human label variation. And I did this also because there is a huge literature in that referring to that in different ways, like perspectives, human uncertainty, hard cases, disagreement, and so on and so forth. If we then assume that this is there and we want to use it, so what can we do? Again, there is a large literature in it, and I try to see it into two big camps. One is those who argue that we should resolve it. We should go back to the single ground truth, essentially. Here we might think about, you know, aggregating or integrating it into aggregation methods, or take another approach that filters out data versus embracing this variation. And here we see works that go back to as early as 2008, repeated labeling, and some more recent approaches that use learning directly from soft labels and so on, versus works in NLP, especially, where we still assume one ground truth, but use the distribution as kind of a regularizer for your methods for learning. And I will not go into any results here. I just want to mention some related works, which I find very interesting. So there is the work by Data Maps and Swapna's, also ACL talk. And she showed that, in fact, if you look at data maps and the kind of instances that in the end are in this ambiguous region, essentially you can learn a classifier on just the ambiguous part. So the gray one here. And in distribution, it performs similarly than training it on all of the data, although you only take 1/3 of the data. So that's great. But what is even more striking is if you train on the ambiguous cases, then out of distribution performance jumps up. So that helps to get better generalization performance. And I think this is really related. So we took this idea of data maps as well. So this is Mike, and he looked at, hey, can we essentially distinguish this boundary here from hard to ambiguous cases in order to come up with an acquisition function for active learning? And he proposed cartography active learning for doing so, where we kind of rely on data maps learned from little data. I think this is further evidence that learning from human labor variation is interesting, but there is a lot of open challenges. So there is a lot of research which is fragmented in different areas, methods proposed, not tested across the board. So we don't know what's really robust yet. We also lack data sets. Hopefully, if you do your next annotation project, think about releasing also your unaggregated data. There is interesting connections to learning from different amounts of labeled data, and there is a lot of unexplored work. I think there is potential here to go to, human-computer interaction and other areas to draw and look on how they pose or work with annotators and so on. But at the same time, there is also evaluation is a big issue because we focus often on easy evaluation. And we need to go beyond, because many of the works and methods proposed still then in the end assume that there is a single ground truth. So you learn with multiple annotators, but then evaluate against a single ground truth. Okay, so I think there is a lot of opportunities in this space. Some ways forward, well, we need more data. So please help collect and release more annotated label or unaggregated labels. Here is a data set, a resource that we recently published in order to help people get started with it. But there is also this interesting connection to model uncertainty. And there is a recent study by Davani et al. That shows, in fact, if we compare to this multitask learning approach that they proposed to the original human distribution, it is a better match to the human distribution, in fact, if we try to model this data. Our PhD student Dioris has looked at this agreement from the calibration perspective. So if you're familiar with, you all are familiar with calibration, we know that this is a huge problem in deep neural nets, that they are not very good at not knowing when they, knowing when they shouldn't know, essentially. And so here is a plot where you see that the classifier is very miscalibrated. So ideally, the bars are all on the diagonal, but there is middle confidence, which is here popping out, and otherwise it's underconfident. But if you think about this problem, then calibration still assumes that there exists a single ground truth that you compare to, right? So these bins are based on accuracy. And we examine calibration at the lens of human disagreement. And what we found is that it's actually pretty flawed, or doesn't help us yet very much. So imagine now we use a method to get a better calibrated model, like temperature scaling. We can improve the calibration plot, the reliability diagram, and we can improve the score that is typically used for calibration, like the empirical calibration error, H, here up. But what does it really mean to improve H from 14 down to 3? Right? So this is really hard to interpret. And so what we proposed is to look at the individual instances. And if you have this human annotated data, then we can also investigate how different they are on the instance level. And then what we saw is essentially, we can dig deeper into this reliability plot here by looking at the individual instances. And so we saw that overall here in the lower plots, the model by temperature scaling gets fewer extremely miscalibrated instances, right? So the tail is shorter, but on the other hand, we also see a bump in the beginning. So we also get fewer perfectly calibrated instances. So although we got a huge bump down from Etche, we might not even want this output perhaps. So we want to make you think about how we use calibration these days. And for more results and insights, please come to Joris Talks on Sunday. All right, so let me finish almost up here. Not all human level variation is noise. I think we need to embrace it more in learning. Also evaluation. I talked a lot about understanding and classification tasks. I think some of this is also important for generation. And but we need to identify what are good approaches and how to evaluate in light of label variation is a big open problem. If you're interested, there is a semi-eval shared task on this running right now, so please consider participating in it as well. And yeah, we'll skip over this here to wrap up. I do believe that we, in general, need to enable more inclusive, reliable, and human-facing technology for language understanding. And I've shown you a little bit of direction I think are important. So learning from scarce data, reuse, and then there's other methods like modularity, embracing human label variation, and something I haven't talked about here, but instead of going for passive learning, we need to go to more active human in the loop regimes, and also cooperation with humans in the long run to make the models do what, to exploit their full potential together, essentially. And with that, I thank you for your attention and look forward to your questions.
Questions? I have all the mics. Zero, come and collect a mic.
Oh, I'm getting one here.
Oh, there are lots of mics.
Right.
Yeah.
Oh shit,
Wow.
that's close. Hi, Barbara.
Hi,
Um,
Sarah.
okay, so you talk about learning from scarce data. And I think you're absolutely right, and that's the direction that we need to go in. But is that possible with the current technologies that we have that rely on salience? What do we do?
That's a good question. No, I don't think we can just run, MLM masking on very little data. We might get some gains, not, but we need better objectives, better incorporation of prior knowledge as well, more structured objectives, I would say. So not just the current technology. It's similar than the long former. It's if you scale up to longer text, it's the same method, but does it help you getting better representations? No, and I think the same is if you downscale, we will not get better representation. We will get for sure worse representation. So we need the other ways to find inductive biases that help us with modeling.
All right. Thanks, Barbara, for the interesting talk. I have a thought or maybe some question for you regarding the human level variations. So yeah, I do agree that human level variation might be perhaps give us some insight about the model. But my concerns, yes, it might be like that if we have annotations based on expert annotators where we believe they equally understand about the process of the annotations. And what if they are like, crowdsourced workers? Did you do some analysis about the inter-annotator agreements until which point we can say that this variability can be useful for the model? Maybe if the annotations result in kind of 0.3 kappa score, for instance, is not useful. I don't know. Have you done something like that?
Yeah, no, I didn't do that myself, but there's work on this, of course, in the annotation aggregation literature. But even though, maybe we need to revise the way we are doing inter-annotator agreement, because we assume that that's also applicable, the same kind of threshold would be applicable to every kind of task the same way. At least this is how we often perceive it. Maybe we don't need exactly those metrics or just one again. We need to look at multiple metrics, multiple things. I do think that also lay people can give a lot of useful information. Even experts make errors, and if you ask the expert again, you might get a different answer. So this is a very complex problem that we need to. So my main point, maybe it didn't come so much true, but I think annotation disagreement has been studied a lot only on the data side, but impacts the modeling and impacts the evaluation. And we need to take this as a global problem in order to advance. So there is no clear answer for a score threshold, I believe.
Hi, Barbara.
Hey.
Thanks for the talk. So about variation annotation. at least part of it, most of it comes from the fact the annotators can come from different social demographic backgrounds, right? So for me, it looks like if there's disagreement in annotation, it's because we don't have the full data, right? We don't have the full information about an instance. And so correct me if I'm wrong, but you try to advocate that, oh, we should embrace this variation in our modeling, but wouldn't it be better to instead like try to aim for more personalized systems which actually take into account that social demographic variation? Because in truth, you have one label. It's just that you don't have that in your data, right? So wouldn't that be a better way forward? It's because I think my concern is like, okay, we're trying to make systems that at least try to behave like humans, but in practice, these systems are not a single, they try to do like a washing out like of all an average of all the humans that annotated their data, right? So
Right.
are we doing it? So, okay, so to exaggerate, isn't this wrong? Or is there actually a reason why you should keep doing that? And yeah, if you could comment on that.
Yeah, that's a very good point. I do strongly believe, but ultimately we would go into more personalized system and personalized view, especially in these subjective tasks. So it's very connected to that, and there is even work on, you know, the annotated demographics, and connecting Martin Sapp, for instance, has done work in this direction. It's all interconnected. Yeah, you're right. But I do believe for some, it's always, again, for some tasks that you might want to have more personalization than for other tasks. So in general, I believe there is still value in going to not just go for the mean, essentially, but embrace the variation that you capture. In general, even if you then in the end spit out, you know, don't personalize as well. But I think personalization is a very important motivation for looking at this even more. Yeah, I agree.
Thanks.
Got time for one more question.
So you started the talk with noticing that currently we have to choose from this large search space which language I should focus on, and if I have multilingual models, we have the curse of multilinguality, kind of they start kind of, you know, not being good for any of those languages and so on, and then which domain and which task, right? So the question is, how do you see the way forward? So for example, one thing, okay, if you leave the multilinguality aside, one kind of direction was to say, look, we are going to have just one language model. This is what GPT-3 is telling us, GPT-2, right? And what we're going to do is, well, we're going to look, let's say, maybe in context learning, we're not going to fine tune it. And people currently are saying, actually, why don't we fine tune a prompt? It can be on a continuous prompt.
Mm-hmm.
And now I'm not going to change the model. The huge language model is there, just give you a different prompt. Okay, you still kind of need a library of prompts for every single task that you want to do, but kind of, how do you see the solution?
That's a very good point. Mm-hmm. So I didn't talk about prompting, you saw not much in that direction, because there is a lot of variety in sensitivity to that as well. No, I do think, I don't know, also if you look now with the project, we're looking at dialectal variation and Germanic variants, for instance. You will need to work more. I think we need more work that estimates what's good and tries to find out how to do transfer from not just building one model for everything. I don't think that's the solution. Even GPT-3, if you ask now, do you speak Italian in English? It would say, no, I don't. And if you ask in Italian, it suddenly knows how to, just as a side note. We need more ways to find out when what works in order to even combine smaller models, have more modular approaches, look more at transferability estimation in this space of languages, tasks, domains. Because we often, I still think we need often a target to which we want to adapt to, instead of building the huge cross everything model. So this will be important for applications as well, to find out a priori, okay, to this target, what can I use from this knowledge? In a way, a little bit going back to pipeline, you might say, pipeline of NLP models that you combine in future, perhaps.
let's finish up. I'm sure there are lots more questions. Let's thank Barbara again for a wonderful talk. And our next speaker is Yejin.
This. Oh, okay. It's okay. And first type. No, just a sec. Okay, I need to first. Oh no, this is not how it should be. Just a second. No. Let me do this. Just no. I really need to bring this back here first. And then do this. And make sure this is on. And then move this to the next screen. It has to be done all in sequence. Back here. Share screen. We're almost there. Good. Phew. Yeah. Yeah. Okay, so I'm excited to share my very speculative thoughts about the entire pipeline of NLP. So olden day pipelines, when I was doing my PhD, looked something like this, with a lot of emphasis on supervised learning. Data set you make once and it's there. It never just disappears or become out of fashion. The current day, it seems we have a lot of pre-training going on as well as a few shot prompting going on in the field. So many papers around that. And then we do see relatively less of supervised learning. I do think that we're going to see this sort of a trend more and more, and then a lot more emphasis on the data set and evaluation. And then I would love to see more of these unsupervised approaches. And then a lot more other components such as reinforcement learning, continual learning, interactive learning, as well as knowledge models as a thing, which, by the way, has been alluded by Mark's earlier talk as well. And then decoding algorithms, again, reasoning inference algorithms that we didn't worry as much about with the supervised learning or even few-shot prompting, but they can be really powerful, especially addressing logical inconsistency problems with the neural models. So about evaluation, let me briefly highlight some such work in recent years. So for example, this MEV paper at NeurIPS tried to address model-based evaluation approach for comparing human text and machine text, because it turns out humans no longer necessarily know how to evaluate GPT-3 text when it's so compelling. And then another line of research is try to look at how do we even evaluate the data set's difficulty in a more information theoretic way. So not only we evaluate models, we are now entering an era where we might actually want to evaluate data set or even evaluate evaluation metrics being meta on the evaluation itself. So a lot more activities toward that. But I move a little bit faster here because I actually want to talk about something else in this talk. But data set cartography, I think it was mentioned in Barbara's talk. It was about, again, evaluating on the data set as opposed to model itself. I would like to also highlight Clip Score at NLP last year, which was about evaluation on evaluation metrics. And then we discovered that, in fact, model-based evaluation, even without human reference at all, did better than our Blue Rouge or some other variants developed for image captioning cases based on n-gram statistics compared against the human written captions. So, if you think about it, that's a more natural way of doing it for humans evaluating image captions, in the sense that I don't need your human captions for me to judge whether an image caption generated by machine is good or not. I have my own understanding about the image caption, and so I don't need references, and we are entering a strange era where it's becoming more of the case. Okay, so, but let me also highlight a little bit about reinforcement learning. Up until last year, I used to think that reinforcement learning is only cool for other domains except for language, because we seem to hear about AlphaGo or protein folding and all these other things where reinforcement learning is being truly amazing, groundbreaking, whereas we don't seem to hear as much impressive empirical results coming out of reinforcement learning. So that's what I used to think for a while. I'm beginning to realize that that's because the way that we were setting our supervision training input-output pairs in a very particular way, we're not really permitting really great opportunities for new learning paradigms to actually show improvement. So I think those things will change. Here's one work that we try to do RL for NLP, because a lot of reinforcement learning literature coming outside the NLP field tends to use language for RL as opposed to the other way, but we want something for an NLP, so that's what we do. And in it, we developed new algorithm called the NLPO. If you happen to be familiar with the PPO, that's a language customized version of a PPO that will operate much better for language problems. And if you happen to be familiar with the nucleus sampling, the same idea is being used for that. Lastly, Quark. This is our new NeurIPS work for unlearning. So you don't want to just always start from scratch, which is the mindset of supervised learning. You just start from the scratch. Whereas for human bias we have about racism and sexism, we don't start our lives from scratch again for that. We just learn what's potentially aggressive toward other people and try to respect that. And so we can learn to unlearn. And so we can do that. And in doing so, it turns out reinforcement learning does provide a powerful paradigm, because we may not have input-output pairings anymore. Rather, we have a reward network that can guide our learning. Okay, so that's the mandatory beginning speculative things. But in this talk, I want to focus on this two-part knowledge models and unsupervised decoding algorithms, and how that's relevant in this today's situation, which basically is about David and Goliath, the art of leaderboarding, when we may not have extreme compute that tech companies do have, and can we do impactful research in the context? So we can draw inspiration from all the classical literature, such as The Art of War, which says, know your enemy, choose your battles, and innovate your weapons. We need to reinterpret that in the new modern deep learning context, which might mean that evaluation with realism and scrutiny, especially adversarial out-of-domain distribution and generative evaluation, where it's not about multiple choice, but machine has to generate answers. That's when machines tend to fail, by the way. Choose your battles with new task, harder leaderboards, and then also innovate your weapons through algorithms and data. So in this talk, there are many ways to address this, but I'm going to primarily focus on two things: symbolic knowledge distillation, and there are going to be a number of different case studies, and then decoding algorithms. Some of you might have seen the first thing, which is this causal common sense models, symbolic knowledge distillation. How many of you might have seen this before? Oh, not so many, so that's great. So the premise of this work is that language models are not knowledge models. We tend to use language models as if that's knowledge models because that's the best thing we have. But I think the only reason why that's the case is really because the tech companies are trying so hard to scale up their language models, whereas the community, NLP community at large, are not investing, the same level of effort into building knowledge models. So in our earlier work, we studied with this atomic at Comet, which are basically symbolic common sense knowledge graph, a bit more similar to maybe textual entailment graph from Mark's group. And then neural common sense model, which is built on top of atomic, because that way it can generalize much better for previously unseen examples that these models need to deal with. So graph is built only so that the neural models can train on top. And importantly, up until 2 years ago, I used to think that this graph has to be fully human annotated in order to be any good, because anything open IE-based method may not be able to produce of resource. So We had a follow worker called Comet Atomic 2020 as well. And let me give you a concrete example, just in case you haven't seen before, what this graph looks like. So imagine you get your cars repaired, or X gets X's car repaired. Because you, as a result, you might want to call Uber or Lyft for a ride. You need to pay the bill. Beforehand, you need money, mechanics. So these are sort of like preconditions and post-conditions of the events that you need to deal with. And then there are some object-centric knowledge. For example, money can be used for paying for repairs. But if you really wanted to, you can also forward that into origami. I've never tried that, but this says something about stereotypical use cases as well as just object affordances based on naive physics knowledge about how the world works. And then finally, there are cases in which the central event cannot happen. For example, if you get your car completely totaled, then you cannot get your car repaired. So there are counterfactual contexts in which the central event cannot happen, and so forth and so forth. So we annotated it. We wanted to go pretty crazy with this. So the graph 2 years ago was about 1.3 million common sense if-then inference rules over 23 different edge types or relation types or inference types. So some of these are about causal common sense reasoning. Some of these are about object-centric naive physics knowledge. But anyhow, again, fully annotated. So what good does this provide is that compared to our Comet versus GPT-3, which is so large, it doesn't even fit into the slide, GPT-3 is more than 400 times larger than Comet, which is trained on this graph, whereas GPT-3 read random web text. In terms of the accuracy of common sense inferences, so here the input to the test, the model, is a particular event, and then inference relation type, and then the model has to produce what might be plausibly true. So this is hard to game. GPT-2 off the shelf used to be very bad at this. So 36% of the output was any good, whereas GPT-3 made a huge jump. This is very impressive. We'll get back to this. But Comet is significantly smaller and yet much better. So it does give you some sense of the power of data, especially in this form of a symbolic knowledge graph, what it can do even with the smaller models. So we put these resources out, and people all around the globe do very creative things. So we wanted to improve the resource further because it's really impossible for any 2 or 3 papers can actually build a resource that's forever good enough. So we now resorted to GPT-3 because the performance was shocking for us, but it's just so large, it's almost useless for anybody's computer. So we wanted to make it much smaller, but way better. So is that even possible though? Because the knowledge distillation literature says usually it's the opposite. Well, it's going to be possible because we're going to do something pretty strange, which is that that funnel is actually convoluted one. I'll tell you a little bit more in a bit. But compared to this more conventional knowledge distillation due to hint nettle, in which if you have a teacher model, you want to compress it down to student model by optimizing this cross entropy between the teacher output and student output. We're not going to do that here because, first of all, teacher model is not even common sense knowledge model. It's something else. And we don't want students to be just yet another language model, but rather we want a model of a different type, which is causal common sense model. In addition, the original research was sort of assuming that the output space is classification, whereas in our case, we want it to be generative models of common sense. So computing this exactly would be impossible, but that doesn't matter because everyone does sampling and call it a day. So we do that. But nice byproduct of the samples is that you can connect them up as if they are symbolic knowledge graph. In doing so, maybe I should go back to here. In doing so, there was a critic model sitting that I'm going to mention in a bit that makes a huge difference because without critic, it doesn't work as well. So what we do is basically can be summarized in this graph. So y-axis shows the quantity of knowledge that is in the data set. So Atomic 2020, with respect to only a subset of common sense knowledge, seven items, 7 inference types, was less than 1 million pairs. So Atomic 2020 had less than 1 million. Atomic 10x, if you just use GPT-3 as is, then you can generate so much so that now we have more than 5 million, getting close to 7 million different knowledge, but the black portion is bad. Green is good, black is bad, meaning when you might remember it was about 73% of the time, meaning about 30% of the knowledge that GPT-3 generate is not good. So what do we do then is we train a small critic model. It's based on Roberta, it doesn't matter what exactly. And what we did was human annotation on about 10,000 examples, whether it's correct knowledge or not. Of course, this critic model doesn't know very much about common sense, so it's not very good at precisely classifying whether a knowledge is correct or not. But what it's good at is at least getting rid of a lot of bad stuff. So you see, we lost so much of a good portion, but at least it got rid of a lot of bad portion, to the point that now the accuracy or human agreement on machine generated text looks better than Atomic 2020. So this is an entirely new situation in which now, comparing human versus machine in terms of accuracy or scale, value, or diversity, even diversity, it turns out GPT-3 is more creative and diverse when measured in many different ways. I'm here just showing a unique 1 gram count, but in the paper, we report a lot more. So all around, machine written symbolic knowledge graph winning over human written one in all criteria. So this was a little bit like, this is so unexpected. But anyway, so that also leads to better models in general. It turns out we can also compare models trained on different kinds of knowledge sources. So GPT-3, again, was about 73% good. But if you train student model using raw GPT-3, somehow students get better on its own. I'm not sure why exactly that's the case. But it wasn't as good as the human written Atomic providing as a training data for Comet. But finally, if we use this GPT-3 plus Critic, which together makes a product of teachers that are becoming more critical, then the final Comet does better. And again, this says something about how the larger, the better is not the case, because the final teacher actually used a lot less data than this teacher, loose teacher, which used a lot more data. So quality actually matters a lot more than quantity of the data. So after this work, we actually wanted to try something entirely different, just in case you really couldn't care less about common sense, maybe sentence summarization. How about that? So this is our new EM-NLP paper, where it's a reference-free sentence summarization, because we don't care about human written summary examples anymore. We're going to go reference-free. By the way, in the meanwhile, the new paper from UT Austin says, well, GPT-3 is the best summarizer. Forget about your supervised summarization model, which is maybe depressing, depending on how you look at it. Or maybe it's exciting because maybe you can do this symbolic knowledge distillation again. So what we're going to do is we're going to grind this GPT-3 and then make it not only smaller, but hopefully better. This filter is where we can be creative and do different things. So in this particular paper, we have 3 different layers of filters. It's almost like a water filter in your house. Probably it's a good idea to have different layers of filter. So fidelity filter is based on NLI, the natural language inference model, in particular WANGNI that I'm going to talk in a bit. And then length filter, because GPT-3 doesn't compress very much sometimes, so we don't want those like non-summarized cases. And then information bottleneck filter based on information bottleneck principle. But anyway, the quick summary of how this goes is that we then realized we don't have to do just one-time symbolic knowledge distillation. We can do this iteratively so that the future generation of teachers, the future generation of students can be teachers, a little bit like how academia works. So it turns out the students can become better and better. That's exciting. So the paper reports different types of evaluation, but basically we can improve quality while not losing summary quality, but improve on other sort of aspects. So that's where things are for now. I kind of glossed over a lot of details because I wanted to share yet another entirely different example based on natural language inference. So this is going to be about data set. So it's the quick summary of what happens with out-of-domain evaluation of your favorite NLI model trained on MNLI, that's usually the de facto standard data set, is that they don't do very well. It's like you ideally want to see something close to 100%, but in general, they're all suffering. So what we do, or what we show, is that Wang-Li, which is 4 times smaller than the original MNLI data set, can do better across the board, despite the fact that data set is smaller. So how did we do that? You might wonder, and you're welcome to try this demo at wangli.apps.alenai.org. It does usually do better than off-the-shelf other NLI models, including Biden defeats Trump, Biden wins, that's entailment, and otherwise it's a contradiction. So I got inspired by Mark's example earlier. So how did we create Wang-Li? Is that first of all, Wang-Li means 10,000s of reasoning in Chinese. I felt that there are just way too many English names in data sets. I wanted to just throw in different language vibe to it. And then our assumption for a long time was that, well, humans know how to write this data set the best, but the problem with the human annotation is that they have artifacts. So it's reported by so many different words, which really encourages machines to latch on superior patterns and pretend that it's learning to do the task while it's just learning to hack the data set. So what we do is based on this data set cartography, which basically said that these ambiguous regions, they're the gem. They're the most important region for out-of-domain distribution. And so what we do is we use that idea in order to ask GPT-3 to overgenerate potential NLI examples, and then use this filter, which in this case is basically dataset cartography idea itself combined with human validation. And it turns out it may be like a relatively simple idea, but this does lead to a much better data set because it combines the diversity that machines can generate as well as the human ability to truly understand natural language inference problems. By the way, I couldn't agree more with what Barbara said earlier about human label variation being an important aspect of future NLP. In fact, I would go even one step further, not to say the noise is not all bad, but actually, I personally think all the good stuff is where there's a high variance for a variety of reasons, but maybe we can discuss offline. But anyway, let me do super briefly on this neurologic decoding because the last portion, genetics induction, is going to rely on that. So this work was NACL Best Paper Award, which actually builds on our previous NACL paper with very similar title. In this talk, I'm going to just share these two. This is neurologic something, doesn't matter. So neurologic, pair of neurologic papers. And the key idea is that we hear so much about how larger is the better, which is, on this left side of the slide, but really the classical AI was about search algorithms. It was a big portion. And in fact, even for AlphaGo, we couldn't go very far without this Monte Carlo tree search. And so search might be still important, especially in this era of large neural models. So that's sort of the wishful thought we had. And relatively speaking, it seemed that compared to how much people talk about either prompt engineering or pre-training itself, people were talking less about decoding time algorithms, and then usually just defaulted to use either beam search or some kind of sampling. But I personally believe that this is where a lot can happen. And in some sense, the recent chain of thought paper, as well as a range of new papers in this space, says otherwise. So decoding algorithm can be really exciting place. And in this particular, what we want to do is to be able to respect logical constraints on the lexical items. And if you think about, like, I give you this conjunctive normal form as a logic constraints for you to satisfy, and you have to generate a sentence that satisfies that, you do not need even a single pair of examples. You can do it right away with a pencil and paper, just you work it out, no problem. So maybe we can do that with machines as well, especially through search algorithms. And if we do that, nice thing is that it can take care of lots of different kinds of NLG applications where you might want to control the content of the output. So neurologic decoding in a nutshell is a search trellis. We're not going to go into this. It's too much. But I just say, especially with the time zone difference, I just briefly mentioned that the complexity comes primarily due to the fact that when you have this full conjunctive normal form to deal with, you have to check whether clause is satisfied or not, either reversibly or irreversibly. And that creates a bit of a complexity with the search algorithm, but it's very much doable for computer scientists. In fact, the first author, Shiming, is the undergrad student at UW, just got out of algorithm class, really good at this kind of stuff at the time of the paper writing. And then because neurologic decoding is not able to look at the future, so imagine your task is write a sentence with a 3 words, car drives snow. Very easy for you. If you ask a neural network to do that and then use the naive decoding algorithm, after writing, I drive my car during it might want to say summer instead of winter, but because we want to deal with the snow, winter is a better choice because we can project into the future. So that's a very classical A-star search algorithm situation. And so we do A-star ask decoding though, because it's not possible to come up with admissible heuristics with neural language models when projecting to the future, which means we have to come up with some approximation, and the details are not very important, but we tried greedy look ahead or beam search look ahead. I'm just being very predictable here, but also sampling look ahead. So these are pretty obvious things to try. And it turns out the detail doesn't matter too much, but in general, it's a good idea to look ahead. So let me highlight the papers together present a lot of evaluation, but let me highlight one simple task, common gen. So this is a task where given lexical constraints, you have to satisfy the lexical constraints in the output. Again, you can do this right away. So if you look at coverage, this is constraint satisfaction coverage, the higher the better. And then x-axis is the model size. If you look at blue line, that's what we used to do with the sequence-to-sequence models is through beam search or greedy search, whatever your conventional search algorithm you want to use. So the larger is the better. That's the trend that we always hear. But it turns out if we have a properly written neurologic decoding search algorithm, then coverage is always 100% or close to that. Whether you use neurologic on top of a supervised model or off-the-shelf unsupervised model, it doesn't matter. Reasoning algorithms can be that powerful. We don't really have to pretend that neural network somehow through this large parameter space, some logical magic pops out. I don't think that's actually possible. And then in terms of rouge emitter, which do correlate with this particular task, again, larger the better for blue line. But if you have neurologic, then it's generally much higher. So much so that unsupervised neurologic outperforms supervised approaches. Not only that, unsupervised neurologic on smaller network can outperform supervised approaches on larger network when using conventional beam search or something. So I do think that we might be collectively neglecting the power of reasoning algorithms. And then in case you might think, oh, but common gen sounds like a made-up task. We also evaluate on things like constrained MT, table to text generation and stuff like that. Okay, so I did that only because I actually wanted to do this, generics induction. This is yet another example of symbolic knowledge distillation. And what we wanted to do is that I wasn't happy about the reliance on GPT-3. I just wanted to do without GPT-3. But that's really difficult to think to even dream about when GPT-2 is just so bad. So here the task is to be able to generate some correct knowledge about a concept. So bicycle, bicycle may have 2 wheels and stuff like that. What we do is basically neurologic decoding in order to lexically and syntactically guide the GPT-2's output so that it looks like a plausible generic statement, meaning don't do storytelling, don't give me convoluted sentences, just give me one simple sentence. And then it says nonsenses like bicycles are also pedal, whatever them is. So GPT-2 is so bad. Like, why are we even trying to deal with this? Well, because we're kind of curious whether we can actually beat GPT-3 using just GPT-2. We do this kind of a symbolic knowledge distillation. So the paper is coming soon, like we're almost about to archive now, finally. But long story short, it looks something like this. So generics KB, which is based on mining web data through OpenAI style mining. And if you imagine just mining web text, people don't necessarily say generic statements for everything in the world, which means it will be noisy. So it was about 75% good. And also quantity-wise, it was not very large. If you pull from GPT-2, you can truly overgenerate. And with the help of neural logic, accuracy is about 40% good. But with a critic, we can throw away so aggressively so that we now have a much smaller amount, but still larger than anything ever existed before, and then still much of a higher quality. And now the final question remains, which is, how do we compare with the GPT-3? Especially when it keeps getting better, by the way. Like when the original GPT-3 was much worse, but now red line is the GPT-3 instruct. Last time I checked, it's really impressive because precision recall curve stays around 80%. It's really impressive. But GPT-2 plus symbolic knowledge distillation, etc., can do even better, which is exciting result in the sense that maybe it doesn't have to be all about GPT-3 and 4 and 5. Maybe there are other ways to get there as well. So to close, actually, I do think scaling laws are for real, though, and the denial is futile. Because, I mean, the amount of common sense knowledge that GPT-3 somehow acquired just by mask prediction is phenomenal. And also, I just love playing with these models. However, I do think that scaling laws only explain the necessary condition, probably not the sufficient condition. It's very important to highlight the fact that it's not the sufficient condition does not mean that it's not necessary condition, by the way. It's like most likely super important factor that we cannot give up at all. And GPT-2 had to be reasonably big enough. I don't think I can actually do the same symbolic knowledge distillation using GPT-1. So the scale is real. I want to say something about the current paradigm of deep learning again. So for a long time, it was either supervised or unsupervised, self-supervised. And this looks really powerful for leaderboards, but it doesn't work if we are doing evaluation that requires model to generate output, like abductive reasoning, counterfactual story revision, all this fun stuff that we trivially do. Models still fail to do this, so there's something odd about it. And in fact, if you think about how humans do learning, then you cannot possibly imagine taking a deep learning class in which professor has no textbook, no lecture, and just give you a lot of multiple choice questions with the correct answer marked. And then you complain that I cannot learn like this. Then the professor gives you lots of Python code or some other language code that you've never seen before, and you have to self-supervise. And this mode of learning doesn't work for humans. And how is it that we are hoping that somehow machines are able to do that? I don't think that just works. I realized I used to think supervised learning when we did this all the time. Actually, let me skip to the next one. When the field had the supervised learning as a big portion, I used to think, oh, that's a natural way of doing machine learning. And then when I see unsupervised learning papers, I used to think, what an unnatural way of doing machine learning, because all that there is maybe like clustering and some grammar induction that doesn't work as well as a supervised case. But now I'm beginning to realize that supervised learning is fundamentally broken because a lot of the tasks don't even correspond to input-output pairs nicely. It really forces us to define problems based on labeling, which I don't even believe that much anymore, especially even with a simple task like natural language inference. There are cases when you realize that I could do entailment or contradiction at the same time, even if it has nothing to do with my personal background. You'll be amazed at how many such examples actually exist that we are choosing to ignore. So we are fixated about making it as classification task, no matter what. And so there's a lot more outside the supervised learning, and I would love to see a lot more less supervised learning of different varieties in the coming years. And in this talk, as a one way to get there, I talked about symbolic knowledge distillation, because in my mind, language models are not the same as knowledge models. We shouldn't just rely on tech companies to create even larger GPT, whatever for that, and create our own potentially, because it's going to be smaller and better. Okay, I'll stop here and thank you.
Wow, thank you, Eugene. We could probably unpack that into about a 4-hour version, but any questions on the distilled version?
Okay, so maybe I can go to your last remarks, right? That I totally agree that this is not how we learn. We don't learn from 1 million annotated examples just to know whether the sentiment of this movie review is positive or negative, right? It's not how we do it. And there has been made the point that a much better learning framework is to learn from natural language explanations, and kind of many people are working in this direction. And to me personally, one of the impressive things of GPT-3 is that it actually shows us that you can learn in this way, right? And if you think about it, initially, what did we have? We had rules, manual rules. Okay, then we had some kind of supervised examples, and then we had deep learning, which basically works in the same way. But now kind of we have a different way of learning that actually kind of you can work from natural language explanations, and typically something that we didn't think was possible before. And of course now you also have like in context learning and all that. It's not clear how far you can push it, but do you think this is moving us closer to the kind of to the natural intelligence and kind of to a universal machine that can actually solve different kinds of tasks? This is what we as humans can do.
Yeah, that's a great question, which is also somewhat philosophical. I believe that it's like that's the right direction personally, because just supervised learning framework in the classical version, at least, it's just so limiting in so many ways. The fact that GPT-3 does strikingly well with instruction-based few-shot learning also says something about the power of the data, because it's a little bit opaque what exactly they do. But based also on other research, actually my colleague Hannah Harji-Sherji and others at AI2 have worked on natural instructions as well as natural instruction 2.0, also known as supernatural instructions, in which if you actually have such a data set where instructions are human annotated for like maybe thousands of NLP tasks, and then train T5, much smaller model on that, then the model actually does better with a quotation mark, quotation mark, for previously unseen task within at least that data set split. The data is not really matching probably what GPT-3 was trained on, but it really demonstrates the power of data. And also the power of reinforcement learning that they're also using internally because they want to incorporate human feedback. I also do think, when we think about how humans invest into education material, even though there's a deep learning paper, someone else writes yet another, or NLP textbook, maybe I should say. And I think it's a wonderful thing. And maybe that's sort of like what I think about the data set going to the future, where I allocated really a lot of real estate here. The exact portion, by the way, is up to my artistic rendition, of course. So I don't know what the major portion is, but I do think that creating somehow different declarative description of what data, what task we want to deal with might be a really exciting future, as well as knowledge graph, as well as other kinds of annotation. As much as I don't believe in supervised learning, I believe in a lot of data, especially complex annotations, that allows us to maybe optionally train a little bit on such data set, but primarily for evaluation of hard tasks, such as what Claire mentioned earlier about document level event understanding. If only we have such a data set, I'm pretty sure that GPT-X whatever will not work very well. It's just deep understanding fails still on especially larger document.
Did you do a comparison when you have the critic and before and after the critic, did you do a comparison about sort of inferential power of the two models? What I'm thinking is, if we say simplification, that these big language, the LLMs are mostly kind of memorizing a bunch of facts, and they do a little bit of generalization, quote unquote, on the sides, and that gives them a lot of error. So you kill that error, right? So you're losing some of that generalization because we assume everything it gets is true, right? And so you're losing some of its little micro generalization, which is killing. That's what you get to the right there. Does it at the same time also improve the true generalization so it can do new things, or is it just killing out the error and just not doing anything more fancy?
Great question. So because I was moving so fast, here we just see the end data for the moment, but what we end up doing is training a neural model on top of that graph, as if it's just linearized text strings. And so if we train model on top of cleaned data versus uncleaned data, and then test their performances on previously unseen common sense situations, because we always only test on previously unseen cases, then we do see that the generalization itself becomes better when the data set is cleaned. So here, this is showing without cleaning. The last bar is with cleaning. And here's actually one reason why that may be the case. So the way that this common sense is produced is through sampling. It's not based on beam search, because beam search leads to degenerate text. So when they're sampling, and GPT-3 may or may not truly understand what I want, so it says things, and sometimes it's a little bit awkward. And it may be because of a randomness to it, or maybe it truly didn't understand the task. So it could be because the model didn't actually know the common sense correctly. It could be because the model didn't understand what to do with this prompt engineering, or it could be because the randomness just pulled out wrong data. So we don't know which is the case. Whereas if we train model on top of this common sense knowledge graph, somehow it seems to reinforce the correct style of language, as well as the content of knowledge being more correct. That's very hand-wavy, speculative thing I could say about this for now.
Okay, I have more questions.
Yeah.
Thank you very much. My name is Mohammed Yaqub, one of the faculty here, but I am a computer vision person. So in computer vision, we care a lot about continual learning, where you touched on a little bit. You spoke about that. Maybe in NLP is a different story, because in vision, we have a huge change on images, video quality, and so on. So can you comment on that, the effect of continual learning for the NLP domain? But my real question is, maybe the larger the model, the better for the sake of continual learning. What do you think about that?
The larger models definitely do learn much faster on a new task based on much fewer examples. So that's just a given. They do have a much better generalization power over different domains. So I think that's why I think scale is never going away, even if we try to develop algorithms that can sometimes match the performance of GPT-3. Having said that, I think a continual learning is not necessarily what I see a lot in the NLP field compared to, say, broader AI or robotics or even computer vision. When I mentioned that a particular phrase, I was imagining something like, oh, maybe a language model looks at images and then, continue to learn through different mode of learning framework. And then sometimes it unlearns some of the things that it learned in the past that needs to be updated, and then keep going on just like humans through this life cycle of learning. And in that context, large models are probably better if you only want to compare simple transfer learning based on model size difference. But there may be other things we can do on top where we insert more reasoning or more different kinds of something else, like knowledge distillation, whatever else.
Thank you.
Yeah.
One last question from Mohammed.
Yeah, thank you very much. A very interesting talk. In one slides, you had a Chinese name for one of the data sets. So my question is actually related to that, not to that particular data set, but actually to somewhat the portability and multilingual aspect of the work. I don't know if you have thought about, okay, so you build like these large common sense data sets and so on, and you exploit them in very interesting and useful ways. Meanwhile, if you go to a language other than English, you can translate these data sets, for example, and you build like resources with them and so on. But there are also these challenges of, people talk about indigenous communities, for example, having different ways of knowing. And so it's not like a one-to-one mapping between, a set of, norms and ways of knowing and knowledge, and so on from one language to another. So if this work were to be done, for another language, what would be the types of challenges that you can imagine having there, other than, the huge amount of work that is invested in creating these resources? So that's part one of my question. The other part, very quickly, I don't know if you have time, but you talk about decoding algorithms, and I also I'm thinking about okay, does this translate right away to other languages? And we know that the structure of languages are different and so on. So I just had these two,
Yeah, that's a great question. I think doing Wangli for Korean language might be possible, especially these days, because they do have a Korean language models. But for other languages for which they don't yet have large language models to pull the data from, or even like MNLI data set in their case, then if we just need to rely on machine translation and have humans correct, it may be one reasonable step, but probably not as satisfactory. So I guess Barbara emphasized the importance of multilinguality as well as more sparse resources sparse situations being important aspect. And again, it seems like unsupervised method or not fully supervised direction is truly important. And my personal hope about, especially just about NLI, is that I wish we come up with a truly unsupervised approach that's not even relying on MNLI, but it's not trivial to think about how exactly do that for broad scope of entailment. The Mark's talk earlier about finding those cases from data was interesting, but yeah, this is an interesting question. About your other question about maybe, the diversity of norms and cultural norms and their influence on language models. And I do think that especially when we worry more about these human label variation cases, high human label variation cases is where, this is where things are more actually interesting and matter to humans. And so we do somehow need to find a better way to really support value pluralism. Because there's no one gold label. I used to believe that there's a true label for any language problems. I no longer believe that. I mean, look at reviewer number 2, who didn't understand my perfectly written paper because they have a different understanding, different interpretation. And oftentimes it's very reasonable what they're worried about. So I started really believing that we need to somehow address the pluralism of really a lot of everything. And how exactly do we do that? It's an open research question, but part of it might be that we may need to get out of this supervised learning mindset where everything has to be input-output, and then everything must have a high human annotation agreement, because by definition, a lot of language tasks do not have a high human annotation agreement. Even for PhD admission, it's not the case, the same university. I mean, every university goes for the same person. And that's a wonderful thing that we don't agree. So that diverse, students get to work on diverse set of problems. So.
Wonderful, a great point to end up on. So thank you again, Yejin. Lunchtime. So lunch, again, will be served up in the courtyard or in the visitor center. The Phil will walk us across, so if we can get back by 1:15 to kick things off again, that would be great.